This conference will now be recorded.
Welcome to this tutorial on characteristic mode analysis, where I will attempt to share some insight into the workings of characteristic mode analysis and also some ideas around workflow and using some software available. So CMA is widely used for a range of different areas in antenna design and placement, including things like antenna size reduction and feeding optimization, or coupling into the ground plane or platform where the antenna is mounted to sort of improve the radiating properties. Ideas around bandwidth optimization or radiation pattern shaping and polarization. And finally, also more common now for MIMO applications, especially with 5G, seeing a lot in this area. We're also seeing a lot more use in other applications like EMC and radar cross-section. So a quick overview of the tutorial today. I'm going to begin by reviewing quickly some concepts and parameters that are relevant for CMA. And then we're going to dive into an antenna example in the form of a demo, where we're going to start off looking at the ground plane structure, just sort of a standard CMA analysis, and then look how an antenna can couple into those modes at different frequencies. And finally, build up a MIMO configuration for a Modal excitation concept. So to start off, once you've run a CMA simulation, there are various properties or results that you can look at. These include a modal current distribution and modal radiation patterns, so quantities for each mode, as well as values like the eigenvalue, modal significance, and characteristic angle. So very often when we are working with CMA, we are interested to know when a mode is resonant. And this is defined by either the eigenvalue equal to 0, the modal significance equal to 1, or the characteristic angle equal to 180 degrees. So if we look at the graphs on the right here, we can see, for example, mode 1, which is this blue curve, would be resonant at the crossing of 180 degree for the characteristic angle, or when the modal significance is equal to 1. So that is about 2.6 gigahertz. So we have those three parameters that give us similar information, and ultimately you can decide which of those you prefer to work with going forward. And it's also worth noting that a resonant mode is likely but not guaranteed to be excited at that resonant frequency. In other words, if a mode is resonant, it is more easy to excite it, but it is no guarantee depending on the structure that you use. Finally, when we include an excitation, so for example, adding an antenna to the structure, we have two further parameters available. The first is the modal excitation coefficient, which is a measure of how easily the excitation was able to excite a given mode. And finally, the modal weighting coefficient is the overall modal presence. So that is essentially a combination of the modal excitation coefficient and the modal significance. So I've highlighted these two parameters in orange here because these are the parameters that I prefer to work with. So modal significance is nice because it is always bounded between 0 and 1. And the modal weighting coefficient is very valuable when working with antenna structures because it tells you what is really happening with respect to the modal presence on the structure. Then some notes on mode tracking in FEKO. So basically how the tracking works is the modes are calculated at the first frequency in the simulation, and then they are ranked according to their modal significance. And this is also when the modal indices are assigned. So in other words, at the first frequency, you can see here, this blue mode has the highest modal significance, so it is assigned mode index 1. Green would be the second, so it's mode index 2, and so forth. And then as the simulation continues throughout the frequency span, the modes are tracked and the index is assigned accordingly. Then just some concepts to be aware of with respect to modal mode tracking. So we don't have time to go into it, but just be informed of the modal cross avoidance concept, where sometimes in mode tracking you can see, let's say, unexpected behavior. And for some applications that cross avoidance behavior is actually a physical phenomena. So that's something to be informed about. And another, let's say, a tip is when you know that you are working with more resonant structures, it can be beneficial to refine the mesh, especially on the edges where the modal current distribution will have high gradients. Or alternatively, you can also reduce the size of the frequency steps that you use in your simulation. And that can improve the accuracy of the mode tracking. Then FEKO also stores the untracked mode data, and if you want to work with this directly, you can also plot that or export it directly in post-FEKO. So if we start off briefly talking about workflows around characteristic mode analysis, I always like to think of these three different steps. The first being more understanding the structure that we're working with, what kind of modal behavior occurs naturally on the structure at the frequencies that we are interested in. And typically there we're going to be looking at the modal significance and also the modal currents on the structure. And from this analysis, we can start getting an idea which modes would you like to work with, which modes are more resonant, or if we want to do some kind of pattern shaping application, are there specific modes that exhibit characteristics that will help achieve the pattern that we want. So this is sort of a first investigation of the structure, and we may not necessarily include the antennas at that stage. But certainly in the second stage, we start to include the radiating structure or the source. And at this point, we start looking at how the antenna will couple to the modes that we want to excite. We may move the antenna to specific positions to try achieve certain modal excitation. And at this point, we're going to be working extensively with the modal weighting coefficient, because this tells us how successful we were in our attempts to excite certain modes. So quite often this becomes sort of an iterative step where we may try something, look at the results, and maybe tweak our design slightly. And we go through that a few times until we are satisfied with the modal weighting coefficients that we have achieved. And the last step might be some kind of verification of the design. So have we met the design specifications? These might be, for example, in something like S parameters or beam width. So those parameters are not necessarily computed with the CMA analysis. So we might do a final simulation here to verify that the specs have been met. Now, characteristic mode analysis, one of the common benefits of this approach, let's say over traditional optimization, is that we do learn a great deal of insight in in the application that we are busy with, where optimization often gives us sort of a single answer. And I just thought I would show this before we go over to the demo, because it's quite a nice example where the insight from the characteristic mode analysis gives a much better understanding of what is actually happening. So it's a very simple application, basically a monopole antenna placed on a ground plane. If you remember, some very early mobile phones may have looked like this. And the positioning strategy that is applied here is designed to excite mode 1 in our frequency range, which it has done, as well as excited 2 other modes in the same range. So this approach could be quite good for some kind of pattern shaping, or maybe even a MIMO application. And on the right now, I'm just showing you a different concept where, instead of following approach to select or excite a specific mode, we now move the antenna to a new position where what we get is that many modes are excited in this case. So obviously, again, if you're thinking of an application like pattern shaping, this would certainly complicate things. However, meaning that it's quite difficult to work with so many modes. However, where things become interesting is if we start looking at the bandwidth of these two cases and compare them. So using the same antenna on the same ground plane at 2 different positions, we can achieve almost a 20% improvement in the bandwidth. So we can see this very clearly in the S parameters, but also worth noting is if we look at the shape of our modal weighting coefficients, we see, like the modes on the left are sort of more narrowband, and there are fewer modes, where on the right we have wider band excitation and obviously multiple modes. So this is an interesting idea where CMA gives us a bit of understanding that we wouldn't necessarily get if we just looked at our S parameters for this case. So without further ado, I'm going to switch over now to our demo. And we're going to look at an antenna example. But before we get to the antenna part, let's look at our ground plane structure. So I'm going to start off just modeling again here a nice rectangular ground. This is around about the size of a modern smartphone. So CMA is used for many wireless applications, and that's why we often use this as our starting point. So the first thing that I mentioned is you may want to refine the mesh slightly on some of the edges. So we can select my geometry, and I can do that quite easily, selecting the local mesh size here. We could choose, for example, here a 5mm triangle size. Then another trip that I haven't mentioned yet is when we're working with symmetric structures, we know that many of our modes might be or might have symmetric characteristics. So what we can do to sort of enhance the behavior is we can set our symmetry in the 2 planes in this case. And what that is going to do is it's going to force or guarantee that my mesh is also symmetric, where even if my geometry is symmetric, it's not necessarily going to be, or it's not required to be meshed symmetrically. So this is sort of an additional step towards that. Then I'm going to choose my characteristic mode analysis. We can choose or ask 10 modes. This is quite a good default value, but it really depends on the structure you're working with and maybe the size of the structure in wavelengths. As the structures get larger, they will more naturally support higher order modes, and you may need more or to request more modes here. But for this case, this is more than sufficient. So I've requested 10 modes, and I'm also going to request my modal currents. And I just need to set my frequency. I'm going to go from, in this case, 600 megahertz to 2 gigahertz, and I'm going to use 21 frequency points here. It is quite a wide band that I'm analyzing, and this could be considered quite a large frequency increment, but we know in this case that the structure is very simple and we don't expect any narrow band resonances, so it should be more than sufficient here. So if you're not familiar with characteristic mode analysis, just pointing out here, in any other simulation, you would typically have to define a source or an excitation, but characteristic mode analysis looks at the natural resonant behavior of the structure, so a source is not required in this case. I'm going to mesh the geometry now. And you can see, again, because of my symmetry planes, that the mesh is nicely symmetric in these 4 regions. I'm going to launch that simulation. I'm just going to save the model here. So that should run rather quickly. And while it's running in the background, I'm just going to launch post FEKO so that we can extract our results. Interesting, while we're waiting here, I'm going to plot using some macros that require the full simulation to be run. But in general, in FEKO, you don't need to necessarily wait for all your frequency points to be calculated. You can already start using post FEKO before your simulations are complete. Okay, so here's my structure. Or the first thing we're going to look at is the modal significance parameters. And I'm going to use a macro that I downloaded from the Altair Connect website. And this is a nice little tool that just helps me plot my characteristic mode parameters. I'm going to choose the modal significance in this case. I'd like to plot it over frequency. 10 modes is what I've requested. And I'm not interested in the untracked modes. So I'm going to run that. There we go. So here you can see kind of the classic behavior for such a structure. So starting off in the low frequency where we have kind of no resonant modes, and then at around about 900 megahertz, our first mode is resonant, and only sort of quite a bit higher up in frequency do other modes become resonant. So let's have a look at the modal current distribution. I can just double click on that now. Typically what I do is I look at the instantaneous magnitude. I like using dB, and we like looking at the vector direction of the current. So I've turned on show arrows here, and then we can start looking at the different modes that occur. So our first mode, or most significant mode at 600 megahertz, is our long mode that runs along the length of the ground plane. Second mode is going to be the short mode that runs across the ground plane. And as we go on, we see the different and more higher order modes. So we have our rotational mode, the cross mode, and then the sort of half resonant mode, and again, sort of a double rotational mode. and so forth. So the idea that we had to make things a bit more interesting for this example, coming back to the modal significance, is we're going to look at, using this ground plane, we're going to define or design an antenna that works at 600 megahertz, at 900 megahertz, and at 1800 megahertz. Basically 3 frequencies where we have very different modal significance behavior, just to sort of shed some insight in the mechanisms with how these modes are excited using the antenna and showing the different parameters that are involved. So I'm not going to go through the whole modeling exercise, but let's switch over to this post-FEKO session where I have prepared some results. So here you can see the model. It's a PFA antenna placed on the long edge of the ground plane. And at 600 megahertz, it's not a very practical design. The antenna is almost the same length as the ground plane, but it's more of a sort of conceptual idea that we want to demonstrate. 900 megahertz, the antenna is a bit smaller. And finally, at 1800 megahertz, it's quite small. Okay, so let's see now what happens when we run this analysis. Again, remembering we have added our excitation. I'm going to go back to my CMA plotter. So previously we looked at the modal significance, but now I'm primarily interested in the modal weighting coefficient, and I'm going to plot them over frequency. I'm not interested in untracked. And for now, we're just going to extract 4 modes. I'll show you why in a later moment. And also, just while we're talking about modal significance and modal weighting coefficient, it's worth noting that if we ran these simulations over the original frequency band, the changes in the modal significance by adding the antenna are typically quite small in a case like this. And that's also why it sort of motivates the use of the modal weighting coefficient, because it shows the actual modal presence after the excitation is included. And I think that'll become more clear now when we start looking at these results. Okay, so here's my, so what I did accidentally, let's say, was I plotted the 1800 megahertz first. That's not the end of the world. I'm just going to select those and change all of them to the 600 megahertz band. And here we can see our results. So the other thing I like to do when working with modal weighting coefficient is I often view it in dB. So I'm just going to copy that and apply it to the other 3 modes. And the reason for that is the numbers are typically quite small, and it just gives you a bit more visibility in how the values differ. So let's have a look what's happening. Basically, at the 600 band, with that very large antenna, we are able to excite mode 1 quite well. And we have a few other modes lower down. So the idea that I often apply is introducing some kind of threshold, meaning that the amplitudes of these modes, in this case, say minus 20 dB or minus 25, are so small that the contribution is almost insignificant, so we can kind of ignore them. And what we should maybe do is just check if there are any other modes that have larger amplitude. And as we go down through the indices, we see that all of the values are very low. Okay, so what we can do now, again, is I'm just going to copy, duplicate these. And then we've decided that we only need the first 2 modes for, sorry, I just deleted the wrong thing there. We're only going to use the first two modes for the 600 band. I'm going to switch to the 900 band there. So now we see a few more modes are present. I've got the numbering all wrong here. Change that to mode 4. So again, if we work off our -20 threshold, we see we've got 4 modes in this case that are above and contributing to my behavior. Let's just go down again and see if there are any other modes that are relevant. So that's below -20. So here we see a small contribution from mode 7, and it's only in the top of the frequency band. Also very small contribution. Okay, so we can leave that where it was. I think it was on mode 3. So there's our behavior for the 900 band, and immediately what we see is we have more modes that are excited now. Instead of like one mode that is excited very strongly, we now have 2 modes. That's mode 1 and 2, the purple and pink graphs here, that are excited over the band, and then 2 other modes that are less strongly excited. Going to duplicate again, and now finally our 1800 megahertz band. So here, let's just check the ordering. Okay, so we've got, if we look again at our threshold, so both yellow and green are below the threshold, so we can start climbing down the indices to see, okay, that one works quite nicely. We've definitely got a contribution. Mode 6, also very nice. And basically what you're going to see here is that the behavior is very similar to the previous scenario, where as we've gone up in frequency, basically more modes are excited. Remembering our modal significance plot from the ground structure previously, where at this higher frequency there were more modes present that were close to resonance, and this basically illustrates that that they're essentially easier to excite. So this mode we can basically ignore as well. I'll just disable that. So there we have our 3 antennas. Starting with a single mode that's excited at 600 megahertz. Here we have 2 modes that are excited quite well. And in the higher band, depending on the frequency range, it's difficult to say which modes are most prevalent. But certainly we have many more and a combination going on here. So one important fact to mention here as well, if you remember, we spoke about mode tracking at the beginning, and I mentioned that the mode indexes are assigned at the first frequency in the simulation. So the point here is that these are 3 different models that are run in 3 different simulations. So the point that I'm trying to make is that mode 1 for this simulation, even though the structure is fairly similar, is not necessarily mode 1 at the higher frequency. And we can see that if we now look at the structure. So this is the 1800 megahertz simulation, and here you can see mode 1. So it does have some component of that long mode, but there's also certainly a horizontal component too, and that's sort of null across the diagonal. And I think if we go to mode 2, this is looking a bit more like mode 1 from the original simulations, but being at the higher frequency, we do see a lot more sort of higher order modes. This is now mode 3, which is definitely our short mode across the board, and so forth. Let's have a look quickly at the other models. So maybe we start with 600 megahertz. So here I think it's very similar to our starting point. So this is essentially our long mode, and kind of a rotational mode. And here at 900 megahertz, we have our long mode and our short mode. Okay, so now we're at this point where we have 3 different antennas. We can see some behavior that we have some explanations for, but it's quite difficult to go from seeing these graphs to actually having a comprehension of your actual behavior. And certainly when we come to a multi-mode environment like in the higher frequency band. So we have another application macro that we can use for this, which is called the CMA synthesis tool. This is also available for download on the Altair Connect website. And basically what that does, I'm not going to run this now, but I'll just show you the user interface. This tool allows us to combine the modal current and the modal far field and near field, if you have those, for multiple modes. So yeah, you can basically, in a scenario like, if I can get rid of that, I can move that out the way. So if we look at our lower band, you might only want to work with mode 1 and mode 2 here because these are the dominant modes. Or in this case, in the higher frequency band, we've got mode 1, 2, and 5, 6, 7, and 8. I think those are the modes, yeah. So we can select exactly which modes we want to combine and basically synthesize the modal currents and the modal far fields. And it gives us a better picture of the actual, like, true response of the system. That is in the synthesis definition mode. I'm going to show you some results from that in a moment. But just to mention that there is also a design mode. So if you, again, are working towards like a specific pattern shaping behavior, you can, using this mode, choose the modes you want to combine, but also tweak the weighting of each of the modes. So it's sort of a kind of a weighted synthesis, where here the synthesis weighting just uses the modal weighting coefficient. So it's kind of the natural weighting. Okay, so let's have a look at some of the results from that calculation. So firstly, starting off in the 600 band, 600 megahertz, you can see firstly so this is a sum of mode 1 and mode 2. You can see also from the labeling here. And as expected, kind of, we have a very strong long mode or dominant long mode because of the mode 1 presence here. And this gives us a almost dipole-like pattern, which is slightly off axis with respect to the null. So nice omnidirectional behavior. As we go up now in frequency, let's go to our 600 megahertz band. I'll just get rid of that for the moment. So at 600 megahertz, we have mode 1 and 2, and 3 and 4 less strongly coupled. And what we see is we still have kind of a long edge on the one side or close to the antenna, but this is sort of a more, call it sort of a higher order or amalgamation of these multi-modes. And that very clear pattern that we saw at 600 megahertz is less prevalent. in the current modal current summation, as well as the pattern, which still has dipole-like behavior, but it's a bit directional on the one side towards the antenna and less so on the other side. Finally, at 1800 megahertz, we now have a combination of all 6 modes here, where the weighting is shown, and what we get now is the sort of almost a double resonant mode when combining, and equally this has distorted our pattern, so we no longer really have that omnidirectional behavior. We can see a bit more directivity towards the bottom of the ground plane, and we now have another null in the pattern, and that is obviously because of the nulls on the ground plane as well. So it's a very useful tool, to sort of bridge the gap from cases where you're dealing with multiple modes and trying to visualize how the pattern, either the modal current or the near field or the far field, will actually look. Okay, so the last example that we're going to look at now is, again, if we work from the scenario, so let's go one step further and say, okay, we want to work in the 1800 megahertz band, but we're not happy with the outcome that we've achieved here. So we're unhappy with the pattern or the modal behavior. Is there anything that we can do? And the approach that we're going to follow is we're going to work on a MIMO design. And the concept is really, if we think, let's say that the goal is to excite the long mode that runs down the length of the ground plane. And we know that if we have a single antenna here, it couples quite nicely into that long mode. Can we do better than that without exciting all those other modes? And the way forward there is to use multiple elements. So we've got 4 MIMO elements. And the question now comes, do we need to do anything about phase? Should we feed them all in phase, or do we need to change the phase to get the current distribution that we want? So if we just think logically from that perspective, like if we have a single antenna, it excites that mode. So by introducing a second antenna opposite it, that tends to excite the mode that runs up the board. So logically, we can maybe guess that we need a 180-degree phase shift so that these 2 currents are in phase. And similarly, these 2 antennas will both excite the current that flows down the board. So it's not necessary to change our phase here. So just to demonstrate that in a bit more detail, what I've done is I've set up 2 configurations where I'm simulating the in-phase case and the out-of-phase case. So to do that, I've gone over here and chosen sources per configuration. That means I can have different source settings for each configuration. And in the first configuration, all 4 sources have the same phase, so 0 degrees. Where in the second configuration, I've introduced a phase shift. So this is over here. It has a 0 degree phase shift. If I go now to the bottom, I've got 180-degree phase shift, and its neighbor is 180, and similarly, the first neighbor is 0. Great. So let's see what we get from our simulations. So again, here you can see our modal weighting coefficient, and I've compared the two cases side by side. So on the left, we have the 180-degree phase shift, so kind of the expected behavior. And I've also simulated the case where we expect won't work as well. So the out of phase case. So where things are slightly confusing here is, so we spoke about the long mode. Because we're now working at a higher frequency, the long mode is no longer mode 1, and that is actually mode 4. And I'm going to show you now when we look at the current. But basically, so this 180-degree phase shift approach does succeed in exciting mode 4. And however, it also excites mode 7 and slightly also excites mode 10. So all these other modes that you don't see in the graph have very small amplitude. And on the right, then you can see the case with the no phase shift. So here we show excite mode 1, and I'll show you in the current what that actually looks like in a moment. And we also excite mode 9 over here. So if we go over to the modal current distribution, so this is just for the excited mode. So here you can see very nicely that long mode, in this case mode 4, that we wanted to excite using this MIMO configuration, where here mode 1 is this sort of dual resonance where we have a null that runs down the center of the ground plane. So finally, as we did previously, we want to try and visualize the actual behavior when we have, in this case, 3 modes, or in this case, only 2 modes. So I'm going to use the synthesis tool and sum those modes. So on the left, again, we can see mode 4, mode 7, and mode 10. And clearly here we have that sort of dominant long mode, but some small null on the short edge, and a pretty nice omnidirectional radiation pattern with no nulls. It's a bit of a dip there. And here, where we don't introduce that phase shift, what we get is basically a null across the board. We do have those longitudinal components, but I think they're opposite in direction. And this gives us the pattern that we can see on the right here, which now has several nulls. So that was the conclusion of the tutorial. I hope there was some insight with respect to characteristic mode analysis, and as well as using FEKO to solve this kind of problems. And should you have any questions, please feel free to email me. Thank you very much.